Cool. Welcome. Glad you've decided to interview with us. We have one interview question for you, which is, say I were to go to a browser and type wikipedia.org and press enter. What happens? What happens? Ivan's like, does he want us to talk about the keyboard and
I was starting with the keyboard.
interrupts and
Yeah, we have an interrupt when you hit the key, and from there you go from the whatever bus, and I think there's a special place in memory where this will
that would
be.
also be a fun interview. Hey, I actually like these interviews, even though, I mean, I like them in the context of small companies because you don't have to worry about like all the different interviewers being synchronized and avoiding bias and whatever so much. But you can just like pull a thread, and it's always interesting to see what people have expert knowledge in, even if it's keyboards. Why not? But no, for the sake of this exercise, let's say, what is the first network protocol that is used after we press enter? So maybe there will have had to have been other network protocols that maybe some of you are familiar with in order to like get us to the point where we can even use the internet. But let's say, well, that's done. I've pressed enter. We are going to use network protocols from here. But what is the first one that's relevant to us?
We use DNS because we need to find out the IP address of the web page.
Yeah, so we have wikipedia.org, which is what we've typed, and we need some IP address for that.
But the protocol for accessing DNS records isn't it TCP over IP?
That's a good question. We are going to make it. We are going to make a DNS query. We are not going to use TCP. You can use TCP. TCP is mandatory for some operations in DNS. If you're maintaining a DNS server, there's something called a zone transfer that you have to be quite familiar with, and this uses TCP connections. But it is recommended, and almost always people use UDP for DNS, basic DNS queries and responses. Should we talk about that in a second, why UDP is a good choice for DNS? First, I want to make sure we understand why we're using DNS here. So we have...
Yeah, I'd love a refresher on that.
Yeah, let's talk about the first things. So we have wikipedia.org. We want an IP address. DNS is going to be our mechanism to do that. DNS is a network protocol. We're going to have to go over the network to do this. It wasn't always this way. We used to have a local copy of the entire mapping of host names to IP addresses back in the good old days. I mean, I say we as if I was there, but before I was born, actually around about to the time when I was born, I guess that tells you how old I am. You would actually just download a file called host.txt that had the full mappings. But these days, a lot of people are on the internet, and a lot of people are using HTTP and email, SMTP, and so on, in particular, that utilize DNS. So we need this mapping. But, well, it's kind of worth asking, like, why bother with this step in the first place? Why couldn't we just do addressing using one of these schemes? Why do we have a way to address based entirely on host names like wikipedia.org, and a totally separate scheme for addressing based on IP addresses? It leaves us in a situation where now we need to do this translation all the time. Like, imagine how many DNS queries are flying around for everything that needs a host name. Couldn't we have avoided the whole thing? What do you think?
Well, I think IP has some really nice properties, right? It's hierarchical, and it's very easy for computers to go from like, oh, I need to go from this one place to this one place. Downside for humans is that IP is not very legible. Like you change one digit or like one bit, and to a person doesn't look very different, but it could send you somewhere completely different. So
yeah. IP addresses are totally unusable. IPv4 addresses, they're just 32 bits, right? Even if we write them in this kind of janky dotted decimal form, 4 decimal digits from 0 to 25, even then it's not very usable. But like, think about, does anyone know what an IPv6 address is? How big one of those is?
It's 128 bits. Is that correct?
128 bits, 128 bits. So totally unusable for humans. So we couldn't have used that for the human usable layer. Okay, so the only way to kind of unify these would be to say, hey, why didn't we just use host names for routing? That's what the IP addresses are for. And Ivan's pointed out that it's nice to have some hierarchy so that routers can look at the prefix bits of an IP address and use that to forward in one direction or another. So that's nice. You could have figured something out like that with host names. Host names have hierarchy as well, like org, wikipedia.org, foo.wikipedia.org, and you can do that arbitrarily from right to left. But it's nice to be able to decouple that hierarchy, which is really about authority for names, from the actual like topology, the layout of routers on the internet. So, and historical reasons. IP is older than DNS.
Also, like, what does the just being bits, does that make routing, like the routing hardware, faster, better, than if you had to deal with strings?
Well, I mean, you could think of the string representation of these bits, but because we want human readable characters in host names, there's some loss there. Whereas if it's arbitrary bits, then you've got more that you can represent in fewer bits, a little bit. Cool. All right. So that's why we have DNS. Someone needs to construct a DNS query. And if you haven't seen a DNS query before, this is a binary encoded protocol. It's not like HTTP 1.1 where you can get / whatever. You need to pack the bytes in here for the request, but ultimately somewhere in here is going to be encoded wikipedia.org, a record, class internet, and that is a query. It's going to have a header. There's going to be this message. Okay, question is, who is responsible, which entity in our system is responsible for constructing this message?
Is it our operating system?
Operating system is a very good guess. A lot of the time, the operating system is going to be responsible for constructing our queries. In this case, it is not the operating system that's responsible, although it can feel like that depending on your use of library functions. We'll talk about in a second. But yeah, Ryan, were you going to say something?
Oh, I thought it was the browser.
Yeah, the browser should be constructing this. So here, if you haven't seen this model before, this is the very poorly named, overused model of, not applicants, I'm back in interview mode, application. Model of network protocols where we consider layers of protocols which utilize the underlying layers. So here, for historical reasons, we'll call this layer 7. And here are protocols like DNS, also HTTP, SMTP. These are all like IETF ratified, like appear in RFC kind of open protocols, but also things like, let's say, BitTorrent, which is open but not standardized in the way that the other protocols I've mentioned are standardized. But also, let's say, Skype, right, which is not open, is a proprietary protocol, is also doing something specific. Right? So we're going to have thousands of these. And basically, if you were to open a network socket and you're not following someone else's protocol, you're in effect creating your own application layer protocol. You're using all the underlying layers to get something across the internet, if that's what you're doing. But the particular use of those underlying layers, that depends on your application. This is an application layer protocol. It's the responsibility of the application, the DNS client, the browser, the email client, the BitTorrent client, the Skype client, or server as well, to implement this protocol, to construct the query, to parse the query, to respond to the query. These are the client and server respectively. Questions about this? Okay, under this is the transport layer. And this is what we briefly mentioned. In the OSI model, this is layer 5, sorry, 4. Let's never talk about layer 5 and 6, please, no questions. This is TCP or UDP most typically. Okay, we'll come back to all those. But for now, we have a DNS message that needs to be constructed. Theoretically, it's the responsibility of the browser, Chrome in this case, to construct the DNS message. Making DNS queries is so common that there is a C standard library function that a lot of people use. Now, just because it's a C standard library function and it probably ships with your operating system does not mean that this is the operating system doing it. It is not a system call. Let's just have a look at it so that you can read while I talk. Yes. So here's the function signature: get adder info, pass in a host name, and well, ultimately you get back you're populating a struct. So this is if you're not so familiar with C, you need to, because you can only have one return value. The return value is an integer here, which is success, and then you're giving a pointer to a struct that gets populated with the results. All right. So sorry, this is the one. Res. Okay, so it's a C standard library function. We're looking in section 3 of the manual. It's not a system call, although it will have to make system calls in order to perform this responsibility of actually doing the resolution. So it's going to construct the DNS message for you and then actually send it out over the wire as well. And what you're going to get returned is the result of this. Just because DNS is so common that everyone would like to use this and would like to have a shared cache and things like that all over the time, shared configuration. And so this exists as an option, but this is kind of an exception. Like there's no equivalent for HTTP, for instance. There isn't like a C standard library function that makes an HTTP request for you. It's always just up to you to construct. Yeah, Eric.
Is some of this kind of convention? For example, I could imagine a different operating system, this being a system called DNS. Like why did Linux or Mac or whatever pick TCP as the layer where we say, no, applications do not have to work at the level of TCP and stop at DNS?
Yeah, it would be tempting to give you a just so answer of like, this is what's extra special about the transport layer. And so this needs to be in the kernel and other stuff doesn't need to be in the kernel or something like that. But a lot of it is historical, and something to demonstrate that is like, where does TLS go? Does anyone know where TLS goes? Well, firstly, do you all know what TLS is? You all use it every day. You may know it as its former name, the more descriptive SSL, the secure socket layer. That was Netscape's name, and then when it became official, they renamed it because committees, bureaucracies. But with the TLS, the secure socket layer, what you're doing is you're opening a socket, which you require the operating system to do for you. So that's a system call. And then you do a bunch of stuff in user space in order to have that socket, the communication over that socket, be secure. So as far as the application is concerned, after that, let's say you want to do HTTPS. That is to say, you want to do HTTP securely, encrypted, and with all the other features of TLS. Well, you open a TLS connection, which is like opening a socket thanks to the kernel, and then doing user space stuff so that all of your messages subsequently sent over that socket are encrypted. And other stuff, have an HMAX and all the other things you get with TLS. Okay, why is that in user space? It doesn't strictly need to be in the kernel. Yeah, so you can make that argument. Like the kernel should have things that like wouldn't be safe to have in user space. Like, would you agree that TCP needs to be in user space? Well, it would be reasonable to disagree with me, but does anyone want to make the case, like, why does TCP or UDP, sorry, did I say user space in the kernel? Why does TCP need to be in the kernel?
Total stab in the dark. Maybe it's just like the abstraction that you're writing to a file or something. So the like OS at that point is concerned with like any metadata that it sets up.
It is nice to have the existing like file descriptor and file like system call interface for sockets, but TLS gives you that same abstraction. Now you got a secure socket, it is kind of needed to have that implemented in the same place where the file descriptor handling and so on is implemented, but you shouldn't necessarily need that.
I had an idea. Is it related to ports? Like ports are what map a connection to a process. And if the user space process can change whatever port it says it is, you can read someone else's connection.
Yeah, like what's the alternative? Let's say you've got two networked applications running on one machine. You've got a database server and a web server or something. They're bound to two different ports. They should receive messages for their own bound port and not for the other one. So the operating system can be there as an intermediary and forward on only the messages that each process should receive. What's the alternative to that? Everyone receives every message and they just ignore the ones that are not meant for them. It's like you can imagine a scenario where that's acceptable. And you can open a raw socket if you've got permission to do that and receive other people's packets and ignore them or respond to them, do what you want. But it's like, this needs to be explicit and we have a way to turn that off, turn off that capability and so on. So you can make the argument that TCP more or less needs to be in the kernel for that kind of security. But you could also make the other argument that like we managed to do the raw socket thing. We could have found another way to do it. With the TLS, it's like you don't strictly need it to be in the kernel, but doesn't everyone more or less want to have this functionality? Wouldn't it be nice to have this trusted code and not have situations like Heartbleed, the OpenSSL bug, where a lot of people were using this user space code maintained by not very many people who are not very well supported, that affects everyone who uses TLS pretty much, or at least we're using OpenSSL for TLS. And maybe it shouldn't have been a user space library. So, anyway, kind of complicated question, not necessarily not necessarily required to answer the question of what happens when, but yeah, it is a kind of historical and contextual, particularly like what's in the C standard library and not get outer info. That's a kind of historical quirk. We could have done without it. It's just a lot of applications would have had to do more work. Okay, the main thing to take away from this previous conversation is that the application itself is responsible for implementing the application layer protocol, which involves packing the bytes however you want. The operating system is not going to support thousands or tens of thousands of protocols, and some of them are going to be proprietary anyway. This is up to you to implement. That's the DNS message. Okay, questions about that? All right, so I'm showing you get outer info. You may also see on the internet get host by name, which purports to do the same thing. It's discouraged. Use of get host by name is discouraged. You can see the man page of get outer info and get host by name for the distinction, but you should be using get outer info. All right, so DNS message is constructed. We are at the stage now where the DNS message needs to go, we want to go out over the internet, and we want it in particular to kind of focus the question, once it arrives at the destination host machine, how are we going to have the operating system at that machine direct it to the DNS server? What needs to be added onto our message, which so far is basically just wikipedia.org a record? What needs to be added onto this, prepended to this, in order for that routing to work when we get to the final destination?
I guess the UDP header.
Yeah, we're going to need a UDP header. And in particular here, we'll need a destination port. Happens to be 53 for the, in the case of DNS, that's just a pre-agreed upon port number. Needs to be pre-agreed upon because otherwise, how would you know what port to put there? So that's the destination port. We are using UDP. So we mentioned this previously. A DNS query like this almost always is going to use UDP. Why is UDP a reasonable pick for this? Like, don't we want DNS to be reliable? Isn't the one thing that you learn about the difference between UDP and TCP the fact that TCP is reliable and UDP is unreliable? That's like the stock standard interview answer. Totally disrespectful to both UDP and TCP to just characterize it in this way. But
I think in this case, like we don't really need a connection. We just need a
just send it out, and if it fails, send it out again. We don't need retries or anything like that.
Yeah, that's the retry logic, right? It's like, oh, well, it didn't work. Let's retry it. The retry logic is literally just retrying. Why is TCP known to be like the retrying, the like reliable delivery protocol? Why is reliable delivery a substantial, challenging thing that TCP is like successful at solving? Why don't they just retry it again?
Does that have anything to do with the ordering of packets?
Yeah, well, what's the ordering of one packet in our case? Well, to not take this for granted, this is small. So typically we're going to be able to send around 150 bytes in a single packet. And this is going to be our maximum transmission unit typically. And a DNS query is going to fit in there, and a DNS response almost always is going to fit in there. And so for DNS, we have one packet. Let's say though that you're sending an image or a video or something over the internet. That is going to be hundreds or thousands of packets that are related to each other, and that should arrive at the destination process in order without duplicates and with no gaps. And that's what's challenging. So TCP firstly does segmentation, is splitting a large thing into smaller things, into segments, and then giving them numbers, sequence numbers. And then based on which ones are arriving and which ones are not, it is retrying. Both parties who are participating are retrying, retransmitting. And there's sophisticated logic around things like how long do you wait before you retry, and what happens if the same thing arrives multiple times, and so on. How many should you retry at once? This is all the kind of interesting parts of retrying. Retrying one thing, you could all implement that, right? So UDP is fine for that. And then UDP, because it doesn't have any of the other features of TCP, has a very small header, and more importantly, in our case, does not require an initial handshake to establish a connection. Right? If we had to do a TCP handshake in order to use a connection, then we would have an additional round trip time for a DNS query. Again, think about all the DNS queries that are happening all the time. We do not want to have that additional latency to look up a DNS record. Yes, Ryan. Ryan, you're still on mute.
Sorry about that. I wanted to ask about like the reliability portion of TCP. Is it because like bits get flipped on the IP layer, and I think what TCP and UDP do the same thing, I believe, which is the checksum, the once complement checksum.
Yep.
Which is like helpful, but like bits will still get flipped. Like one out of 1,000, I want to say, or something like that. So then is it like in practice, like most application layer services also do their own version of like reliability with like checksums and bits getting flipped and stuff?
In practice, most don't. In practice, most don't. I mean, think about think about when you implemented a web server or something, or like even like you wrote a web application, you received something, you just trust that what you receive by reading on the socket, what you've gotten from the operating system is correct. Like very few people will implement an additional checksum there. But there are some. So if you're using TLS, for instance, there is something called an HMAC, and that is an additional digest that's included with messages. That in effect, if you have a change to the message and not a corresponding change to the HMAC, then that's an indication that there was something wrong with that. So, and that is an application layer protocol, even if your application layer protocol is sitting on top of that. So there's that, and there's lower down as well. If the bit flip happens at a point where the link layer protocol can detect it, like between when one Ethernet card sends it out, goes over the wire, and another Ethernet card reads it, then Ethernet will handle it at least better than what IP or UDP will handle it, because of the cyclic redundancy check that Ethernet has. So it's only if it's after that, like if it's sitting latent on a router between one network card and another, that's when the bit flip the IP checksum or TCP checksum is going to check for us is relevant. So there are other checks. We don't usually do it at the application layer because we assume that it's okay by then, even though we're sometimes going to be wrong. It's just like trying to use stats to our advantage. Any other questions before we proceed? Okay, we have a destination port in the UDP header. What else would you expect there to be in the UDP header? Well, now we know there's a ones complement checksum as well, so it counts for 16 bits.
We also need a source port.
A source port, yeah. Why do we need a source port?
We have to tell where we want to read our information from.
Yeah, it's a return address. So the DNS server should put as its destination port our source port so that it gets back to us, gets back to our process once it has arrived at our machine. So remember, ports are a kind of multiplexing, demultiplexing device for the kernel to say, hey, of the 100 processes here, which of the processes should get this message? And it's like an apartment number. After you've gotten to the right apartment building, it's the final piece of the address. That's UDP. To be clear, TCP and UDP are both going to have source and destination ports, and that's kind of the unifying thing about them, and the fact that they both have this checksum. Cool. I think we've said this already, but just to make sure, which entity in our system is responsible for constructing the UDP header?
In this case, the browser.
The UDP header?
Oh, no, that's DNS. UDP would be the operating system.
Yes. Yeah, so we're going to go, apologies for those who've gone over this previously, but we're going to construct a socket. The browser is going to construct a socket by making the socket system call. It's going to specify that it's an internet socket, and the type of socket is going to be, in this case, SOCDgram, because that's what we're sending, a datagram in UDP. If we were sending a stream of data, which is more than one packet, we'd say sock stream, and that would give us a TCP socket. So once we have that socket established, and by the way, what do you think calling the socket system call does when you have a TCP socket? Like, what does the operating system do for you? Like, you construct a socket, but you don't actually send anything.
So you mentioned the handshake part of TCP, and I'm wondering if that starts with the socket creation or the first send, because I could see it both being reasonable.
Yeah, it's not the socket. Well, if you think about the signature of the socket system call,
Oh, yes.
like who is it going to send to?
You're right. We don't have an IP address yet.
Yeah, and with TCP, you're usually using the send system call, which doesn't have an address either. If you were to do send to, then there would be an address. But typically with TCP, you are going to use the send system call, so you need to have made the connect system call. All right, so you make the connection. Calling connect with the address is going to do the handshake. That will do the handshake before you send any messages. And by the way, in protocols like SMTP, where the client does not send the first message, this is how it's meaningful to have a first message sent. The client makes a connection. Once the connection is established, once the handshake happens, the server, SMTP server in that case, can send the first message. Just as an aside. Okay, but we are going to make I should stop saying we, because we changes in this hypothetical, but the browser is going to make a connection. Sorry, it's not going to make a connection. It's UDP. It's going to construct a socket, a DNS socket, a UDP socket. And then by sending its message, DNS message over the UDP socket, that is going to have the kernel construct a UDP header, so that ultimately when this gets to the right apartment building, it can go to the right apartment. So it has the right port there. Okay, but that begs the question of how does this get to the right apartment building in the first place? Like, how does it traverse the internet to end up at the correct machine, the correct host? What are we missing in our picture?
We're missing IP.
IP. We need an IP header, right? What is the most important thing that we're going to have in the IP header?
We will have an IP address, which will tell us, what thing to go to.
Yeah, what is the host that we're going to go to? Let's say the DNS server we're using is Google's public DNS server, and the destination IP address is going to be 8.8.8.8. Yeah. again, we'll need a source IP address again, so that we can get a reply, whatever that is. And then there's going to be a bunch of other stuff in the IP header. IPv4 versus IPv6 is different. It has different features. So the headers are different, but you know, both have, well, they call it different things. But as an example of something else that's in there, in IPv4, you have the time to live, which is really a hop count. In IPv6, it's called the hop count. And it's the number of machines, routers, that this can go over before it should be dropped. Right? So every router along the way should decrement that number as it passes it along. And well, why do we have that? Why is it nice to have a hop count in there?
Prevent some cycles from happening that aren't detected by an individual machine.
Yeah, you could just have a poorly configured network for whatever reason. And if we had no mechanism to drop a packet that was stuck in one of these cycles, then over time, you know, the internet would just fill up with crap, with the packets that are bouncing around, not getting to their destination. Yeah, so hop count is a simple mechanism to say, well, after some number of hops, just give up. All right, so that's IP. Already the kernel is doing our work for us. The kernel is going to do this as well. So the kernel will prepend UDP or TCP headers, and then it'll prepend the IP header. It could be IP, and we're constructing our socket. It could be an INET socket, which would be IPv4. It could be an INET 6 socket, which would give us IPv6, and it's going to construct the corresponding headers for us.
Why does the why does the kernel do this for this part for us? Because it's not like we're not like setting up the, you know, the source port or anything. Like there isn't. Is this just another case of kind of like path dependence, or is there like a reason to put this there?
Yeah, I guess it'd be kind of hard to implement a system where the operating system was responsible for the UDP header, but not the IP header. It's also kind of nice because whenever you're using the internet, you're constructing these headers. It does things like construct the checksum for you. It'd be annoying to do that yourself. It could expose that as a function, just like a library function where it computes the checksum, but it's nice to hand it over. It's nice for the operating system to be able to determine our source IP address. Again, you can imagine a situation where you like query for your own source IP address, and you can do that and put it in there yourself, but they'll be more prone to bugs and to people like easily spoofing their IP address, which you can do anyway. Like all these things where we're like, oh, it's very important that the kernel does it. It's like, well, you could open a raw socket and then, so that's this, and then do all of this stuff yourself, like construct the header yourself anyway. So it is possible to do all these things. But then why is it not the standard way to do it? Well, partially because not everyone's allowed to open a raw socket. You may want to remove as an administrator the capability of constructing a raw socket. And also because it's like kind of work that everybody needs to do. I mean, part of the context of this, these are sockets. Have you heard these being called Berkeley sockets before, or BSD sockets? Yeah, so these, like, it's not just network sockets, because you can also do local communication with them. But they were created as part of the Berkeley software distribution to make it easier to use the internet. And this is part of why BSD and its legacy, like Mac OS, was popular, because people wanted to use the internet and they wanted it to be convenient. And so having this socket abstraction was a big hit. And obviously from BSD, it went to other Unix family operating systems. And then there's WinSock, which is the like Windows kind of equivalent of sockets. So it propagated from there. But it's like the operating system, people wanted the operating system because it had sockets, because sockets were convenient. It's nice to have the operating system do this for us. Not strictly necessary. All right, so we've got our IP address. Once this goes on to the internet, every router will know what to do because it can look at the destination IP address and forward in the correct direction. Okay, but how do we get it from our machine to the router? Or how is it going to get from our router to our ISP's router? Or how is it going to continue from there? Like, what is the next protocol that we need?
The next thing I can think of is MAC address related.
Yeah, we got an address at every layer, huh? So far, at least. So we've got a destination. We need a destination MAC address. Right? Maybe it's going to be the MAC address of my router, right? Whatever that is. Just make something up. Okay, so to be clear, like what are we addressing in each case? The IP addresses, the IP address addresses a host name, usually a single machine, although not necessarily. In a typical case, a single machine, that's the IP address. Within that single machine, there are lots of processes that are interested in the network. That's what the port addresses. But these are the destination. That's like the DNS server machine, the DNS server process. The MAC address that we're addressing now is local. At least it's proximate, right? It's nearby. It's my router's MAC address. Because that's the challenge that we have right now. Physically get this to my router, not to one of the other networked machines like in the local area, like in my house.
Yeah, but isn't the I don't understand how that could even happen, because isn't the IP address that we've identified basically the only, like, it's a singular connection to the outside world, right? And the IP address, the first thing that it's going to happen is it's going to hit my modem, right? And then internally in my network, I have MAC addresses for the machines, or maybe I have like other IP addresses for the other machines within my network, right? So I don't understand why we would need MAC here.
Yeah, we need the MAC. Like, let's say I have this message and I'm just broadcasting it on the local network. We need everything other than my router to ignore the message, and for my router to take it seriously, to accept the message and forward it on in the right direction.
So it's actually the MAC address of the machine that's making the, yeah, okay, got it. For some reason, okay, that makes sense. So my machine, MAC address, and then when this message comes back, it tells the router, okay, send it to Chris's laptop.
Well, you're going to have a source MAC address as well. This is your machine's, maybe I'll do it 99 something.
So why would my machine know what is the destination MAC address?
Yeah, well, it needs to know, and this is going to happen when you just connect to Wi-Fi or something. It needs to, as part of that process, know the IP address of your router. Okay, but that's just the IP address of the router. And generally speaking, very frequently, there's going to be an IP address for which we would like to know the MAC address. So imagine the router's job. The router is constantly getting inbound messages. Imagine like a router in a data center, constantly getting inbound messages that are destined for a given IP address. But in order to physically get it to that machine, it needs the MAC address. So actually resolving an IP address to a MAC address is a very common problem. And there's another protocol for that called ARP. And we can see what ARP tables exist on my computer, actually. And so you can see here this mapping between, these are local IP addresses, 192.168 subnet, local addresses and their MAC addresses that have been discovered. And so there needs to be a protocol of like asking your local network, hey, who has the MAC address for this given IP address? And someone should know, at the very least, that entity who has that MAC address should know that, they are the one that has that IP address. And then this information is shared around. Everyone builds up their ARP tables. This can be an issue if things change. You've got to like flush the cache and stuff. But yeah, that problem needs to be solved. How to actually figure out the MAC address for the next stop, for the next destination, based on only having an IP address. That's ARP, you can look up. Yeah, but we have the destination and source MAC address. What is an example of a protocol that is going to fill out this header? What are the kind of protocols that use MAC addresses?
Ethernet.
Maybe Ethernet is one. And let's just, in each case, we're just picking an example, right? DNS is an example of an application layer protocol. UDP is a transport layer protocol. Let's fill this out. At layer 3, we have the network layer. We still have choices at this layer, right? IPv4, IPv6, etc. If we go down further, we have the link layer, which is layer 2. And we have, again, a lot of protocols here because, like, you can imagine creating a new one to solve your specific problem and still using the internet and still using the layers above it for your overall purpose. And so people create new application layer protocols all the time. But the common ones in use, Ethernet for wired, 802.11, which is commonly called Wi-Fi, for wireless, and then a bunch of other stuff, Bluetooth, Zigbee, etc. If you do IoT stuff, you may have heard of. So a lot of protocols at that layer. All right, let's say it's Ethernet here. Primarily, we have a source and destination MAC address. We briefly mentioned another thing, the cyclic redundancy check, which is like an error detection and 1-bit error correction code. And there's a bunch of stuff that goes into the protocol around, like, how do you space out the messages? How do you synchronize the sender and receiver? Because, you know, you're sending signals over some physical medium, right? It might be an Ethernet cable, like a twisted pair copper cable, or it might be coaxial or fiber optic or something. You need to encode the message correctly for that physical medium, and that's what that protocol is going to be about. Cool. Which entity in our system is responsible for constructing the Ethernet header? By the way, and footer, in the case of Ethernet. That's where the CRC goes.
Your network card?
That's the network card. Yeah, that's the NIC.
NIC.
So the operating system, NIC is network interface controller. Network card, same thing. Or, you know, if someone says Wi-Fi card or Ethernet card, that's what they mean. The idea of calling it a card, it's like using the floppy disk icon to save something. Like, it's no longer a separate physical card that you purchase, take out of the box and plug in to your computer. It is integrated usually into the motherboard, or you know, somehow more integrated with the machine. But yeah, network interface controller, that's what constructs the header.
And so does the kernel, does it have to supply like information here? I'm a little foggy on like where a MAC address, like
the source MAC address is going to come from the card. That's baked into the card. And this is your MAC address is supposed to be some globally unique number that the manufacturer of your network card, like let's say you bought an Apple MacBook or something, Apple built somewhere in the Apple organization, there was someone who built this network card for you and incorporated into the machine that you bought. And Apple has had to take a number from its space of assigned MAC addresses and give one to you that's baked into your network card. So that is something that's set by the network card. The network card is computing the CRC32. The network card is ultimately determining what signal to send out over the Ethernet port. It's bad to call it a port because we use the word ports in a different context, but like the thing that your Ethernet cable plugs into. Like what signal to send over the Ethernet cable, at what frequency, like at what speed, I should say, like how many bits per second. That's all determined by the card. The operating system does give the destination MAC though, right? Like that was figured out from the ARP table.
Okay. And so I guess the fact that this is baked into the NIC, that's why a bunch of these protocols, they all use MAC addresses, right? Or not. I'm assuming there's something out there that doesn't use a MAC address because they don't feel like it or something. But like Bluetooth and Wi-Fi and Ethernet use MAC addresses because it's like, okay, cool.
Yeah, I mean, it started with Ethernet and it was a pretty good idea, and so they all kind of adopted it. And it's nice to have a global space. All right. So this is our message as it's about to go over the wire. it goes over the wire, it gets to my router. What is my router going to do with this message? So we have this, maybe we'll start to draw it out on my computer here. As it's going out over the wire, it has ETH, IP, UDP, DNS, ETH. Gets to my router. What does my router do? What does it look at? What changes? Yeah, Aaron.
Like your router has like a bunch of different exits. It could send a message through. It needs to pick one. So in order to pick one of the exits, it looks at like a table that it maintains of IP addresses to exit names, or I don't know what they're called, but
subnets. Yeah, ranges of IP addresses. Yep.
Ranges.
Yeah.
So it looks at the IP you're trying to go to, references that table, finds a match or a good enough match, and then sends that message out to that subnet.
Yes. Yeah. Now, in the case of my router, it's pretty boring because I only have one ISP. There's only one step that it can take. All right. I could have two ISPs and it would have to make a choice. Or more interestingly, deeper into the internet, most of the routers are going to be connected to dozens of other routers. And it needs to make a decision of what is the next best hop? Like, how is this going to get closer to the destination? And, there could be a number of ways that get it somewhat closer, but ideally it would get the most closer. Like, take the road. Imagine you're driving from the West Coast to the East Coast or something. There are lots of roads that you could take. As long as you don't end up in a cycle, you'll theoretically eventually get there. But it's like you would like to take the road that is going to get you closer to your destination next. So that's the overall problem that IP tries to solve. And the way that it's going to do that is to say each router has a forwarding table that is basically a mapping. Let's say that these two interfaces are A and B. In our case, it'd be a very simple table where we're ultimately saying, this is simplified, but we're ultimately saying there are some subnets. Let's say, we're trying to get to 8.8.8.8. Let's say 8.anything. I'll just write it like this for now. 8.anything, it takes A. Okay, but 8.8.anything, it takes B. Okay, by having a kind of structure like this, we're saying, well, look, 8.something is kind of go east. That's better than nothing. But 8.8.something is like take highway 1. That's not quite right. Take whatever highway takes us more east. Like is the better pick for the highway to go to the East Coast. Yeah. So now this is not how we typically write it, but the subnets are something like this. You'd say 8.8. By convention, you say 0.0, but what we're really saying is that doesn't matter. What does matter is the first 16 bits. So this is how we label the subnet.
Subnet is just like anything that satisfies the condition of like the pattern that you've specified.
Yeah, it's like it's a sub network, but really it's like a logical grouping of IP addresses. Here, 65,536 IP addresses match this pattern. So it's just a way of kind of labeling that group. Right, so obviously we've got a left to right hierarchy here. Okay, so each router is going to do this longest prefix match algorithm, these days implemented in hardware for speed. But we're going to, in this case, match against B, and it's going to go down here. Now, it needs to do a little bit of work. I mean, actually, let me ask that as a question. What changes in the packet? Obviously, the DNS query doesn't change, right? Like why? I mean, ideally, the DNS query doesn't change. If you're a kind of shady ISP, you might do something which is called deep packet inspection. Look at the DNS query and fiddle with it. Please don't do that if you're even kind of shady ISP. But theoretically, the DNS stuff should change. It should say exactly the same. The UDP stuff should say exactly the same. Like, why would the router care about that? What does change?
I guess the link layer stuff could change, right? Like it could fully change. You could be on 802.11 and then it could change to Ethernet, right?
Yeah, it absolutely needs to change, because at the very least, the source and destination MAC are different now. Remember, we were only addressing my router. Now we need to address the next router. So it gets over that link. But now, yeah, it could be absolutely different, right? You could connect to your ISP via 3G or cable internet or something. DOCSIS is another link layer protocol. And then they connect within their network using a totally different network protocol. And sorry, different network protocol, a different link layer protocol. And that could change at every single hop. Why not? So the Ethernet, and this is part of the value of this layered model of protocols, of this kind of encapsulation. We have, let me just make sure everyone can see it on this side. We have the ability to like swap and change the layers with a very simple protocol for how you relate two protocols to one another, protocol for protocols. You just put the bytes of one up against the bytes of the other. You just like put the Ethernet stuff right on top of the IP stuff, or right before the IP stuff. Yeah. And if it's Wi-Fi, well, you just put the Wi-Fi bytes directly before the IP bytes. Yeah, very easy to swap and change. There's not some like fancy interface between them. It's just bytes abutted.
Sorry, I've lost track and kind of got lost in the weeds. How do we know where we're going again? Like
ultimately, it's based on the destination IP address here. As we're going over the internet, in each case, we're matching the destination IP address against the possible subnets, the subnets that we know about at each router.
Oh, right, because we already have a list of IP addresses of like DNS servers, and then that's where that.
Yeah, we're making a DNS query to a DNS server that is already known to us. And there are another set of protocols and systems for being able to find that out that you can look into, like DHCP. If you don't remember configuring a DNS server, you may have set up your ISP. Your ISP would have given you a DHCP address, and that's a protocol that does a bunch of things. One of which is give you an IP address for a DNS server, but you can also manually configure your DNS server and so on. Yeah, that's how we have that first IP address. All right, so this message is going to go over the internet. Oh, by the way, the IP layer stuff is also going to change a little bit, because we've got to decrement the hop counts. And decrement the hop count, and that changes the checksum. So we need to recompute the checksum. So at each router, we're checking the checksum, dropping the message, and sending back an error message if the checksum's incorrect. We're looking at the TTL and sending back an error message if the TTL has gone to 0, well, actually to 1. We don't forward it on if it's at 1. And then recomputing, like decrementing the TTL and recomputing the checksum, forwarding it on. And this eventually should get us to our destination. Okay, the destination is a destination machine. So let's maybe draw it. And it goes over some more routers. We see this is the whole internet, so big graph of routers, and it gets to some beefy server machine. Let's draw as a box, I guess. All right, this is 8.8.8. What happens then? What happens next?
Does that computer just store in memory of that host.txt file you were talking about earlier?
Oh, you're talking about how we actually do the resolution of the DNS query?
Yeah, maybe I jumped ahead and assumed everything was going to get unwrapped at this point.
Yeah, let's talk about that.
Okay.
Let's talk about the unwrapping first, like who unwraps what at what point, because it's arrived as something, some link layer protocol, IP, UDP, DNS. I won't write them all in again, but we have those layers. Okay, who unwraps the link layer?
I mean, I'm thinking this is going to be the opposite of what we just did. So the NIC.
The NIC, yeah, the destination NIC. Okay, and then hands it over to the operating system. What does the operating system do?
Operating system would unwrap the IP header and the UDP header.
Yes.
And
Yeah, and it would like there's like a socket there, right? Or
There should be, hopefully, yeah, an association, a binding between the destination port 53 and a socket opened by a process, which should be the DNS server process on this machine. Right? So the operating system looks at that. That socket would have been blocked. So the DNS server, its job in life is to loop and to read from a socket. So be blocked, waiting for a message. And finally, that message has showed up. And so the operating system can now schedule that process and return from that system call, receive from, and that DNS server process gets just the DNS message, right? Everything is unwrapped. It's like you just got the letter. You know, all the envelopes and envelopes and envelopes, they've all been unwrapped and you just got the letter, and the letter is our original DNS message that we constructed at the application layer. Okay, and then, you know, the DNS server process looks up its database. You know, usually people use this open source bind program, but there are others. It could be a text file, it could be, you know, an in-memory data structure, whatever you wanted, just to figure out whatever app, you know, it's an application layer protocol, you can do what you want. However, you're going to map the IP address that wikipedia.org, the host name, to an IP address. It's going to do that. And then there's a whole lot of stuff that we could say about DNS, how DNS works, but assume the DNS server has the answer. Now it's going to construct the response. But that's going to be all of this stuff exactly in reverse, right? It's going to construct a DNS response, hand that over to the operating system, its operating system, through a socket. Its operating system will construct the UDP and IP header, hand it over to the network card. Network card will construct the link layer protocol, go back over the internet, bounce around, get back to our machine, hopefully. Okay, so after all that, we have an IP address. Yeah, and then what do we do with the IP address?
Set up a TCP connection for HTTP request.
Right, so yeah, we're going to do exactly the same thing over once again, but this time it's going to be an HTTP query. Using a TCP socket, which will result in a TCP header. This time there'll be a destination port of 80, because that's what we use for HTTP. This will have an IP header. This will have an Ethernet header and footer. Same thing. Again, you see the value of layering and of this basic encapsulation, like bytes abutting each other to encapsulate protocols idea, because we're doing the same thing just with HTTP as the application layer protocol instead of DNS. Okay, and we have a choice of transport layer protocols, and TCP is a better fit for HTTP, at least until HTTP 3. TCP is a better fit. It was believed. We do generally, but statistically, most people still believe a better fit for HTTP. And so we use TCP instead of UDP instead, but it's just like kind of choice where you can sub out one for another. And the difference, like to the application programmer, the primary difference, until you get into the gritty details of like performance and the handshake and all these things that you should care about. In terms of the interface, all you're doing is passing a different argument to the socket function, right? You're saying sock stream instead of sock dgram, and now you get to use TCP. How cool is that? How easy is that? That doesn't mean it's simple. And for people who argue that sockets are a terrible interface, they're like, hey, it's easy, but not simple. There's a lot of stuff going on behind this easy interface. You know, it breaks and it's hard to reason about sometimes, and you got to like trace the operating system and stuff. And people who are like, sockets are a fantastic interface are like, look how easy it is. You get to change the argument. It's so easy. So I say that it's one of the most successful abstractions of all time to allow you to judge, make your own judgment about that. You can see that this combination of ideas, the layering, encapsulation, and the socket interface, the operating system's responsibilities, does make things, it makes network applications kind of straightforward to build. Okay, we don't need to talk about this going over the internet because it's going to do exactly the same thing with the same prefix matching as our DNS message. Yeah. Like the routers don't care what transport layer protocol you're using. They have nothing to do with the transport layer protocols, let alone the application layer protocols. They do exactly what they did before. Cool. The great thing about this question is that you could go almost infinitely deep on any little piece of this, but as a kind of overview, the big picture, the story, the life of a packet, the life of 4 packets, really, in our example. Any thoughts or questions about this? Cool.